Hi, today we're going to talk about the nervous system. I'm going to cover a little bit of structure and function. However, you should have learned most of that in anatomy. I'm going to go over communication and organization. Bear with me, I'm still trying to figure out this program. How do I advance the slide? Okay, got it. So let me get the laser pointer. We'll do blue. Oh, and I have to turn it on. Okay. So cells of the nervous system include your nerves. So nerves would be, the anatomy of the nerve would be the dendrites get the signal, then there's a cell body, the axon. Some of those axons have myelinated or myelinated, some of them aren't. Myelinated increases the action potential speed, unmyelinated doesn't. And then you have the axon terminus and then the synaptic cleft. When we talk about nerves, we have a presynaptic nerve, and then a synapse usually, and then a postsynaptic nerve. The presynaptic nerve meets with the postsynaptic nerve. Sometimes there's an interneuron or the nerve in between them, and then we have the supporting cells. Here's the anatomy of a nerve. So if you look at the dendrites in the middle of the screen, dendrites are the receivers of signals, and then they travel to the cell body, and then the axon hillock region, and then they travel down the axon via action potentials and to the axon terminal region. And then this axon terminal region has a synapse, and it's connected to either another nerve or a tissue or an organ, depending on what the signal is. Some of these, again, is this axon myelinated or not myelinated? Okay, and so it's myelinated. So that means that it has a myelin sheath, or the Schwann cells make the myelin sheath, and that wraps around the nerve to provide insulation. Does this speed up or slow down propagation of an action potential? Right, good, it speeds up an action potential. So the axon hillock generates the action potential, and the action potential is going to jump from node to node to node of Ranvier, and so it actually speeds up that action potential. Where do you see these types of nerves, or the myelinated nerves, or the insulated nerves? You see them where you want fast action potential. So for example, for sensory reflexes. Here is a histology slide of them. So here are your dendrites, your cell body, your axon hillock, that's actually how you spell it, Hillock, and then the axon region. Supporting structures would be in the glia, like the glue, think of nerve glue, right? Astrocytes are in there, and then you have the microglia cells, which are actually macrophages, and they immunologically attack things to prevent them from attacking the nerve cells. The goal of nerves are actually to conduct impulses, right? Surprise, surprise. Some of them are excitatory and some of them are inhibitory. We're not going to cover inhibitory ones, we're just going to cover excitatory ones. The types of conduction would be normal conduction, so that means the action potential goes down the axon, and then saltatory propagation would be when you have myelin sheaths and the action potential jumps from nerve to nerve to nerve, or a nerve node to node of Ranvier to node of Ranvier. How do we keep the action potential going in one direction? By absolute refractory period. So once this area, if you look at the picture on your right, once this area depolarizes, then the next area is going to depolarize. How do we make sure the first area doesn't depolarize again? If you look down at the bottom picture, good, it's an absolute refractory period. So because it's an absolute refractory period, that makes sure that this area can't generate another action potential until it gets out of absolute refractory period. So that makes sure that the action potential gets propagated down the line to the terminal region. This just shows saltatory propagation. You should have covered this in anatomy. Let's talk about how that impulse crosses the synapse. Okay, so we've spent time on the last time we met, we talked about action potentials, right? So you have depolarization, repolarization, hyperpolarization, and that generates action potential down the nerve. So if you look at number 1 on this slide on the left-hand side, The axon is depolarized using sodium voltage gated channels. And so these sodium voltage gated channels pop open, sodium rushes in, depolarizes this region, and then sodium rushes in, depolarizes this region, sodium rushes in, depolarizes this region. That's how we get the action potential down to the axon terminal region. Excuse me, let me go over this with you. So this nerve is the presynaptic nerve. This is the presynaptic terminal, which is the axon terminus, right, the end region. And then we have the synaptic clasp, which is the space between one nerve and a second nerve. And then this is your postsynaptic neuron, right? So it's pre-synapse and post. The synapse is only like nanometers wide. It's not very wide. Okay, so let's go back to the axon. So sodium voltage gated channels generate the action potential on down the axon. And then when you get to the axon terminal region, different voltage gated channels pop open. So if you look at number 2, calcium voltage gated channels pop open, and calcium rushes in and depolarizes this region. Okay, once this region depolarizes, then the neurotransmitter filled vesicles, they actually contain acetylcholine, and I'll go over that later. But the calcium causes this vesicle containing neurotransmitter to fuse with the membrane and dump the neurotransmitter into the synapse. We call that what, endocytosis or exocytosis? Right, so exocytosis is dumping out. So you're dumping out the neurotransmitter into the synapse. So that was number 3. Number 4, the neurotransmitter binds to receptor sites on the postsynaptic membrane. So these neurotransmitters bind to receptors on the surface of, receptors on the surface of the second neuron. Right? We call the second neuron the postsynaptic nerve, right? So the neurotransmitter binds to these receptors and actually pops open this channel. So if you have a receptor binding to if you have a neurotransmitter binding to a receptor and popping open a channel, is that a voltage gated channel or is that a ligand gated channel? All right, so that's a ligand gated channel. So acetylcholine binds to this channel, or this receptor, pops open the channel, and what rushes in to depolarize it? Now you might have guessed calcium because we just talked about calcium, but it's actually sodium. So sodium is going to depolarize the second nerve. And then we're at number 6. And so that's going to generate an action potential down the second nerve. So how does one nerve communicate with another nerve? It's via neurotransmitter. So the neurotransmitter gets released into the synapse, binds to the postsynaptic neuron, depolarizes the secondary nerve. There's a misconception though that students have. So I want to talk about that for a second. If you look at the synaptic cleft, so I'm in the middle of the picture, I'm at the 4th receptor, right? Or the 4th channel, ligand gated channel. This neurotransmitter is acetylcholine. So neurotransmitters are how nerves talk to nerves. Hormones are how tissues talk to tissues, or how nerves sometimes talk to tissues. But so this is a neurotransmitter. It's going to bind to this receptor and then pop open this ligand gated channel. And then it gets kicked out of the receptor. And then it binds, pops open the channel, gets kicked out, binds, pops it open, gets kicked out. As long as there is neurotransmitter in the synapse, it's going to keep binding to those receptors and triggering action potentials. So it's going to keep generating action potentials down the line. How do we stop this? Well, first, the first nerve stops getting excited, and then it stops releasing neurotransmitters into the synapse. But there's still neurotransmitters in the synapse. So what ends up happening is these guys get degraded either by enzymes on the surface of the second nerve, or they get sucked up back into the first nerve. All right, and so once these guys are degraded, then they're not going to generate any more action potentials. So I just want you to be aware of that. A lot of times students think that the neurotransmitter just sits on the receptor and is stuck there, and that's not true. It binds and lets go, binds and lets go, binds and lets go. This is an example of how cocaine affects the synapse. So if you take a look in the top middle of the picture, here's your presynaptic neuron, here's a nerve signal, right? And then these are synapses. And we simplify it just showing one synapse. But one nerve can synapse with hundreds, if not thousands, of other nerves in the brain. And especially when a baby is 0 through 5, they're making, or even in embryonic development, they're making millions of synapses every day. And then they, once you get into after 5, you start pruning away the synapses that you don't use. And then once you're hit 18, you go through another growth period until 25. And then at 25 is when you start pruning away stuff, and that continues for the rest of your life. So 0 through 5 and 18 to 25 are really great explosive periods for learning. And if you have little babies at home, you know that they like to stick everything in their mouth. They're always constantly wondering and curious, and sometimes they get into everything, but it's because their brain just wants to know how everything works. Okay, so let's focus. So here's the first nerve, and it's synapsing with the second nerve. Okay, that's the postsynaptic neuron. So take a look at the picture. So the first nerve releases dopamine, and that's a neurotransmitter. And your brain has a lot of different neurotransmitters that it releases. For us, we're just going to talk about a couple of them. We're not going to talk about all of them. But dopamine is released, and it binds to the second nerve and causes an action potential, right? Dopamine is sort of a feel-good chemical. It makes you alert. And then once dopamine is present, you have this receptor that actually kicks it back into the presynaptic nerve. So it transports it back into the presynaptic nerve. How does cocaine work? Cocaine actually sits on that uptake receptor so that it can't pull the dopamine back in. So what ends up happening is the dopamine stays in the synapse. And as long as there's dopamine in the synapse, it can keep triggering the second nerve. And so it keeps generating action potentials and action potentials and action potentials. And so cocaine, one of the things with cocaine is that it gives you a lot of energy, and it gives you a lot of long-term energy. And that's because it prevents the breakdown of dopamine. New antidepressants, so selective serotonin reuptake inhibitors, work in the same way. The antidepressant, or the SSRI, will actually sit on the reuptake protein so that serotonin stays in the synapse longer. And so if it's in the synapse longer, then it's going to keep binding and triggering action potentials so that you feel better. Usually depression, or they think that depression is a decrease in serotonin. And so when you block the reuptake of it, then it stays in the synapse and you keep getting action potentials. And so that makes you happy. Okay, we'll stop there and we'll go on to lecture 2. I want to check and see how this recorded.